at linear inequality in one variable, solve problems, and even down to word problems leading to linear inequality. We've looked at all that, and then we are now progressing, and then um, in like two classes behind, we are looking at inequality in two variables. Yes, and then in that two classes, we were seeing how we can present an inequality problem in a graph. Yeah, is use a graph to show the area that satisfy given set of inequalities. Okay, so you can check out those classes. They are very important to help you in understanding this one we are going to be doing right now. Okay, so having looked at inequality in two variables, we were able to see that we can use graphical methods to show the area that satisfy the solution of given set of inequalities. So, and what that led us to is what we call linear programming, because we realize that we can use, we can use the graph of inequality to obtain maximum or minimum values of an objective function. Okay, that is to say, because in life situations, we come to understand that um, there are situations in business, in agriculture, in other spheres of life that is subject to some constraints. They are subject to certain limitations. So we realize that we can simplify these inequalities, you know, in a graphical way and obtain the maximum and the minimum values of a given objective function. Okay, so look at this problem here. If you check out this problem, you realize that in this question we are given to show the region. That's the first thing we have to do here. We are given to show the region Z that satisfy this set of inequalities. Now, you can apply this set of inequalities in a particular, area of endeavor, whether in business or in agriculture or whatever. But these are limitations. You can see 2 times x plus 3y is greater than or equals to 6. In this case, x plus y is less than or equals to 6. In this case, x minus y is greater than or minus 2. X is greater than or equals to 0, y is greater than or equals to 0. And then this is the objective function. So this is objective function that is subject to these constraints. So we are looking at how we can maximize this function. Okay, that's what we are looking at. And then these are the constraints. This is the objective function. And what we want to deploy is a graphical method of presenting linear inequality. So you follow me as we look at that. The first thing, like in the previous classes I have discussed or we've had, you realize that when you have these inequalities and you want to present them in a graph, what you do, like we have explained in those classes, is you first, please, I will advise you to check the last class I did before this. It was very, very clear there. Okay, but that notwithstanding, I'm still going to give the explanation. Okay, so we write this, we pick the first one, I, and write it like a linear equation. So we have 2x plus 3y equals to 6. And then having written it like a linear equation, we now substitute either x or y to be 0 so that we can obtain the intercept of either x or y. So if I say when x is equal to 0, you realize that this will vanish and this will remain. You realize that we will have 3y equals to 6. And of course, you will see there that y will be equals to what? 2. That is when you divide both sides by 3. You keep that, and then you come back and say when y is equals to 0. We have declared x to be 0. Here you declare y to be 0. And then you realize that if y is 0, this will vanish. This 3y will vanish. And this will remain. We will now have 2x equals to 6. If you divide both sides here by 2, you realize that your x will be equals to 3. So in that graph, the y-intercept is 2 and the x-intercept is what? 3. Okay. Now, we also try to know the area to be shaded. We also try to figure out which area should the solution set lie. Okay, and how we try to find out that I have been explaining in the previous classes is we figure out what is happening at the origin. And you know, at the origin, x is 0, y is 0. So we come back to this inequality and check whether we can obtain a logical conclusion from that. If we say at the origin, you realize that if you put here 0, 2 in bracket 0 plus 3 in bracket 0 is greater than or equals to 6. What can we observe from here? We realize that 0 is greater than or equals to 6. Please, is 0 greater than or equals to 6? No, 0 is not greater than or equals to 6. And because of that, we now conclude that the origin is not part of the solution area. That is, when you are shading, you are not going to shade the origin inclusively. You understand that? Okay, so we can say the origin is not part of solution area. Okay, then let me also look at the second inequality there. We have x plus y. We'll keep this because I'm going to make the graph over here. So let me get all the values, the intercepts I need. Then I'll come over here and put up the graph. So equals to 6. You can see here that when x is 0, of course, y will be 6. And when y is 0, x will be 6 from here. Now, at the origin, we check, look at it, x plus y less than or equals to 6. So 0 plus 0 less than or equals to 6. Is 0 less than or equals to 6? Yes, 0 is less than 6. Okay, this is logically correct. Unlike this, 0 is not greater than 6 and it's not equal to 6. Okay, so here in this inequality, we can say the origin is part, that will be shaded inclusively, is part of the solution. Okay, it's part of the solution. Then I'll keep that one, and I'll also check the third one. I have a third inequality there before. These ones, this is the x greater than or equals to 0, y greater than or equals to 0. They don't need any solving. So these are the major ones. And okay, let me move on. I hope we are taking note of this. Okay, so that let it not be that I am going to obstruct you from seeing what I have done already. Okay, otherwise you take note. Let's look at this. We have here x minus y equals to minus 2. When x is equals to 0, you see that you have minus y equals to minus 2. If you divide both sides here by minus 1, you realize that y is equals to 2. Okay, and then when y is equals to 0 in that, then we will have x equals to minus 2. Okay, let's also check what is going on at the origin. At the origin, you realize that what we have here, 0 minus 0 greater than or equals to minus 2. Is 0 greater than or equals to minus 2? Yes, 0 is greater than or equals to minus 2. That is logically correct. By implication, here in this inequality, the origin is part of the solution area. Okay, so we have got this, three informations that we need to make the graph. So we will now go into making the graph of these informations we've got. Now let's have something like this. Let's have something like this. Okay, and the points I have there. Okay, now the points I have there from this one, I have x being 3, y being 2. Okay, and I have over here 6 and 6, y 6. Okay, let me say somewhere here is let's say 2, 4, 6. Okay, and then over here 2 as well. Do we have any? We have x3. Okay, let's assume 2, 4, 6, so that 3 will be in the middle here. 2, 4, 6, so that somewhere here minus 2, let's say minus 4. Okay, let's say down here minus 2, minus 4. Okay, so if you are doing this is my sketching. If you are doing this using a typical graph booklet, that would be awesome. Okay, because of course this is a typical representation of it. I'm sure if you understood this, doing it in a graph will not be a problem. Okay, so we have this. Now we can now show here that, okay, let me, y here being 2 and x being 3. 3 here, maybe somewhere here is 3. So I can connect them. Another thing is, remember that when we are drawing these lines, for this greater than or less than, we use dotted lines. And for greater than or equal to or less than or equal to, we use thick lines. Of course, if you can check out all these ones, all of them are greater than or equals to, less than or equals to. So we are using all thick lines. Okay, so just a reminder. So we have this. Okay, we have this as the line representing 2 and 3, 2x, 2x plus 3y equals to 6. Okay, and then we have another one. This second one is 6 and 6. 6 and 6. Okay, 6, another thick line. 6 and 6. Maybe I will use another. Let me use this one. 6 and 6. Okay, so this is, oh, this is straight. Okay, so this is x plus y equals to 6. X plus y equals to 6. And then the other one is y2 x minus 2. X minus 2. Let me use another. Okay, that is x minus y equals to minus 2. Okay. Okay, I think we can see clearly the differences in them. What else? We were told as well. Okay, let me start shading. Let me start shading from here, on this particular one. I will only shade the part that contains the entire inequality to make it very clear. Okay, all right. From here, the the conclusion we made says that the origin is not part of the solution, and this is it. So we are not going to look at the line. We are not going to shade inclusively the origin. We are not going to shade this way. We are going to shade away. Okay, so in doing that, I will shade like this. Okay, you might be tempted to ask me, is it that you know earlier on that this is where the solution is going to lie? Is it that you know earlier on about that? But you see that this thing fell in. I could have shaded everything, but I want it to be very clean and tidy. I don't want to mess up the entire space. Okay. Then this is where the solution to this lies. It lies outside the origin. You can see the conclusion that gave us that. What again in the second inequality? At the origin, what is going on? We say that the origin is part of the solution, and that one is this. So the origin is part of the solution. So we are shading inclusively the origin this way, not this way. Okay. So with my this, I will shade this way. I will shade this way. I could have shaded inclusive, but I told you I don't want to mess up this space. Okay. Then what again? What again do we have there? The third one. The origin is part of the solution, and this is the line. So we are shading like this. It will include the origin. You are shading like this. Okay. So I will only shade here. If I had decided to shade others, I will also shade like this. But it's going to mess up the entire space, as I said earlier. So I'm shading only inside within here. Now, what about x greater than or equals to 0? X, this is x, greater than or equals to 0 is this way. Okay, this x greater than or equals to 0 is like this. So if I intended, I can do it just like that, like that, like that. And then we also have y greater than or equals to 0, and y greater than or equals to 0 is like this. Okay, so if I like, I can but it shows that this place, the solution for y greater than or equals to 0 is also here, as you can see, and the solution for x greater than or equals to 0 is also here. Now, if you look at this now, you will see that this 1, 2, 3, 4, 5 inequalities, their solution lie within here. Their solution lie within here. Now, assuming that we want to use the points, the extreme points on this place to maximize this objective function. Let this now be our objective function that we want to achieve. And we want to use the extreme points. What is here? At this point, x is 0, y is 2. So we have here, we can label them A. This is x 0, y, 2. Okay. And here, this is another extreme point. And at this point, I can call it B. And at this point, what's going on here? Yes, x is 3 and y is 0. Yeah, y is 0. X, y. Okay, that's of s, y. Okay, that's how you enlist it. So at this point, let's check what is going on here. At this point, we have x is 6. Let's call it C. X is 6 and y is 0. Okay. At this point, you see that we might not be able to determine what is here. This is the intersection of two linear equations. You see, it's the intersection of two linear equations. So to run away from error, what I'm going to do is to solve this line, which is this, and this line, which is this. Those two equations, I'm going to solve them simultaneously to know the exact point of intersection between the two of them. I'm sure you got what I said now. I will solve x minus y equals to minus 2 and x plus y equals to 6. I will solve them simultaneously. Now, if you watch, the coefficients are equal here. So if I subtract x minus x is 0, minus x minus y minus into minus this will give me minus 2y equals to minus 2 minus minus 2 minus into 6 will give minus 2 minus minus 2 minus 6, which is minus 8. So if I divide both sides now, if I divide both sides by minus 2, I have y will be equals to minus 8 over minus 2, which is 4. So I will come back here and determine the value of x. So if I put y4, either in this equation 1 or 2, if I put y4 here, I will have x minus 4 equals to minus 2. And this will become x equals to minus 2 plus 4. And that is x being minus 2 plus 4 is 2. So x being 2. So you can see how I was able to determine what is at this point. Let me label that point D. Let me label it D. And at that point D, x is 2 and y is 4. Y is 4. Okay. X is 2 and y is what? Y is 4. So because of trying to get the exact value here, I have to solve it simultaneously. I'm sure you understood what I mean by that. Okay. All right. Now we are looking for how to maximize this objective function, and these are the extreme points. Remember where we're heading to. This is linear programming, and the idea here is we are trying to see how we can use this graphical method of solving linear inequality to maximize this objective function. That is to find the maximum value, and we can trace it within these extreme points, Okay, when we are through with that, you can apply it in any endeavor, in business, in in agriculture, to maximize certain constraints, that is within whatever you are checking out. Okay, let's look at this now. Oh, sorry. I had my k is equals to this. Okay. Let's see quickly what we can achieve as a maximum result. In agriculture, that can be a maximum output, given that maybe so space of land is available, so manpower is available. It's a restriction. It's a restriction. So manpower is available, labor force is available, and maybe quantity of input is available. All those things are constraints. What can be our maximum output? So linear programming and the understanding of this can help one to achieve that objective. So let's see what's going on here. Okay, we begin to check at point A. At A, what can be our achievements with regard to this? What can we obtain? So at point A, K will be, x is 0. So we have 2 bracket 0, y is 2, then plus 4 in bracket 2, and that's going to give us that k is equals to 8. Okay, maybe 8 units of whatever you can classify it into. And then at this point, this is another extreme point. At at b at b you can see that k is equals to x is, so we have, sorry, k is equals to, we have 2 in bracket x, which is 3, then plus 4 in bracket 0. So can we see that k is equal to 6 units here? Maybe let me say units of whatever, and then we check also at c. At c, another extreme point. At c, okay, k is equals to 2 in bracket x is 6 plus 4 in bracket 0, y is 0. So we have k equals to 12 units of whatever you are going to classify it into. Okay, and then finally at d, at point d, we have that k is equals to 2 in bracket, is 2x now, 2 in bracket 2 plus 4 in bracket, what we can achieve that there is 4. So this is 2 times 2, 4, plus 4 times 4, 16, and that will give us k to be equals to 20. That is 20 units. 20 units. Now, if I happen to be the one to advise you in a matter like this, what I'm going to tell you from my analysis is that this combination of the combination of how many units of x do we have here? 2. And the combination of y, that is the combination of 2 units of x and combination of 4 units of y, will give you a maximum output of 20 units.